Welcome, and today we are going to discuss relays, both signal and power relays. They are one of the most fundamental switching components in power electronics, and even with all the advances in solid-state technology, electromechanical relays continue to be used everywhere. They're simple, reliable, and able to handle a wide range of loads. SameSky carries several families of relays, and I'll talk about the basics, discuss the difference between signal and power relays, but spend more time on power relays, as power relays have a wider range of ratings and features. I'll also touch on the difference between non-latching and latching relays and when each type makes sense. So let's start with what a relay actually is. At its core, a relay is an electrically controlled switch. Inside, you will find a coil, an armature, a return spring, and one or more sets of contacts. When current flows through the coil, it creates a magnetic field. That magnetic field pulls the armature, which opens or closes the contacts. Depending on the type, when the coil current stops, the return spring brings the armature back to its default position. Relays come in many different configurations, such as single pole, single throw, or double pole, double throw. They also have several timing characteristics like operate time, which is how long it takes for them to engage, release time, how long it takes for them to disengage, and contact bounce, which is how much the contact will bounce between the two states. With that brief introduction, let's separate the two broad categories of relays you'll likely see. Signal relays are designed for low voltage and low current applications, such as communication equipment, instrumentation, and small control systems. They focus on precision and low power. Power relays, on the other hand, are built for larger loads. They are used in HVAC systems, industrial controls, appliances, automotive systems, and anywhere higher current switching is needed. Their contacts are larger, they're built more solidly, and are designed to handle significant electrical stress. While there is a lot of overlap between the two types of relays, I'll focus on power relays specifically for the rest of this video. So within power relays, an important distinction is whether the relay is non-latching or latching. A non-latching relay is also called a monostable relay, meaning it has only one stable resting state. The contacts change position when the coil is energized, but as soon as the coil is turned off, a spring pulls the armature back to its default position. This makes non-latching relays perfect for safety-critical designs because any loss of power returns the system to a known and predictable state. They're simple to use and inexpensive. And the main drawback is power consumption, as they require continuous current to stay actuated. A latching relay works differently. It is sometimes called a bistable relay because it has two stable states. Once you switch it, it stays in that position even after coil power is removed. Latching relays use either a permanent magnet or a mechanical latch to hold the armature. To move it again, you apply a short pulse in the other direction. Because the coil is not energized continuously, standby power is much lower. The relay runs cooler and the coil sees less long-term stress. This is helpful in energy-saving designs or applications where the last known state must be preserved during a power loss. The trade-off is that the drive circuitry is more complex. Applying pulses in the opposite direction means a polarity reversal in the driving circuitry, requiring an H-bridge or a dedicated driver. This can be avoided with double coil latching relays, with one coil to engage and the other coil to disengage, but the driving circuit would still be slightly more complex than a non-latching relay. I actually have two small working examples of a non-latching relay here on the desk. I was able to remove their covers so you can see how this electromechanical relay works. While the exact configuration of a relay changes from model to model, all the main components are there. You can see the coil here, the spring on top that returns it to its normal position, and then the contacts here on the other side, where actuating the relay causes the moving contact to switch between the normally closed position and the normally open position. I want to show this in action so you can see the movement of the contacts. I'm using an illuminated tactile switch from SameSky that I have for another demo video we're working on. You can go learn about tactile switches after we're done here. Right now, the LED in the tactile switch is powered through the relay's normally closed contact. When I press the button, the relay changes state and the light turns off. In this case, when I actuate the switch, it closes, providing power through the coil of the relay. The relay then opens the connection to the LED in the switch, turning it off. We will also be able to see and hear that moving contact make a small movement between the two stationary contacts. Anyway, it's always fun to see what's happening inside these devices. When working with relays, there are several best practices that we recommend to improve performance and reliability. When working with non-latching relays on DC coils, always include a flyback diode to prevent voltage spikes. For both relay types, you should manage inrush current if you are switching large capacitive or inductive loads. Pre-charging capacitors or adding an inrush limiter can prevent large current spikes that would otherwise stress the contacts. If you are switching AC loads, using a zero-crossing circuit to time the relay operation can dramatically reduce arcing and extend the life of the contacts. For latching relays, pulse width control is important. The pulse must be long enough to move the armature, but not so long that the coil heats unnecessarily. Mechanical protection also matters with electromechanical relays because shock or vibration can sometimes cause unintended switching. Aside from those specifics, there are several universal suggestions that would help with any power relay. Always derate the contact current rather than running at the upper limit of the rating. Always take into account thermal considerations and ensure there's enough ventilation or some other thermal path. Finally, consider sealed relays in dusty or humid environments. All of these straightforward recommendations will go a long way toward improving long-term reliability. Now that we know more about relays, the big question is, how do you choose the right relay? Always start with the basics. The coil voltage must match your system, and the coil current must make sense with the available power. Contact ratings must match the type of load, especially when you're switching inductive or capacitive circuits. Check the maximum switching voltage and make sure the load does not exceed this when engaging the relay. Think about the environment the relay will be used in and whether shock, vibration, or contamination are concerns. Finally, decide whether a fail-safe default position is required. If so, a non-latching relay is usually the better option. If holding a state without consuming power is more important, a latching relay is the better choice. And that's it! Relays are simple devices in principle, but selecting the right one and driving it properly makes all the difference in system performance. Non-latching relays are straightforward, predictable, and ideal for safety-focused applications. Latching relays reduce power consumption and maintain their position through power cycles, which is valuable in many modern designs. If you have any more questions about relays, we have several in-depth blogs in our Relays blog series at sameskydevices.com. SameSky offers mini relays of all types, so whatever your needs may be, we have something to fill that need.